Imagine a world where AI doesn't just, chat with you or generate these amazing images on a screen, but actually interacts with and truly understands our physical world.
Mm.
The whole pursuit of artificial general intelligence, AGI, it's moving so fast from just digital stuff to embodied agents. We're
Yeah.
talking robots that can genuinely perceive, reason, and, well, act in our messy, unpredictable environments.
It's a massive leap, isn't it?
Yeah.
And in this deep dive, we're going to take a bit of a shortcut to understanding the real cutting edge here. Vision language action models, VLAs.
Right, VLAs.
And specifically, we'll focus on this fascinating concept called action tokenization.
Absolutely. So our mission today is really to unpack how these, frankly, incredible systems are learning to translate complex human instructions, visual information, into actual physical actions. We'll dig into the surprising ways they do it, why these approaches are so crucial, and yeah, the huge challenges that are still definitely ahead.
And hopefully you'll walk away from this deep dive with a much clearer picture, the core bits and pieces of these future robots. Understanding not just what they do, but how they're starting to bridge that gap between digital smarts and physical doing.
Okay, so let's set the stage. How do we even get here? Let's trace the evolution that kind of paved the way for VLA models.
Yeah, good idea.
You're probably familiar with large language models, right? LLMs like GPT-4, Claude.
Sure.
These are the absolute powerhouses for tech stuff, natural language, reasoning, generation. They really are the backbone of so much AI we see today.
And alongside those, we saw the rise of vision foundation models, VFMs like CLIP and SAM.
Right.
These are showing really impressive generalization across all sorts of vision tasks, understanding images, segmenting objects, really versatile.
And then came the integration, kind of bringing those two worlds together. Vision language models, VLMs, things like GPT-4o, Gemini 2.5 Pro.
Multimodal.
Yeah. Exactly. Multimodal. They can handle both visual and text information, process it, generate content, and they tap into just vast world knowledge because they're trained on internet scale data, images, and text together.
What's really fascinating, though, is that while these digital AI steps are huge, embodied AI, well, that's a significantly bolder ambition.
Yeah, it feels different.
It really is. Think about it. The physical world is just inherently unstructured. It's way more challenging than even, difficult out-of-distribution digital inputs. Consider just the sheer complexity of, say, free-flowing human conversations happening around a robot, or unexpected things happening, cluttered rooms. It's orders of magnitude more complex than even something incredibly difficult like autonomous driving.
Which is already super hard.
Exactly. And autonomous driving, while complex, operates in a relatively more constrained physical space, right? Roads, lanes.
That's a good point. And it's not just the software side, the algorithms. Embodied AI brings in massive requirements for the robot hardware itself.
Oh, absolutely.
And honestly, right now, that hardware is, well, the source material says far from being met.
Yeah, that's about right.
We're talking about needing truly dexterous hands, not just simple grippers. And we lack sensitive, full coverage, tactile sensors, that could feel surfaces properly.
It really underscores that models, data, and hardware, they all have to evolve together. It's a synergistic thing.
Yeah.
And this is precisely where VLA models come in. They build directly on those powerful foundation models we just mentioned to give them action capabilities. VLA sits right at that critical intersection. Digital AI, robotics, hardware, it's a core subfield of embodied AI. And yeah, a key area in this whole AGI pursuit.
It really feels like the next frontier, doesn't it? Taking AI off the screen and into the world.
It is. It's the next great leap in how AI interacts with the real world.
Okay, so let's get into the nuts and bolts. How do these VLA models actually work? There's this core concept, a unified framework. So imagine you've got vision and language inputs coming in. These get iteratively processed by a sequence of VLA modules.
Okay.
And these modules produce a chain of what are called action tokens. These tokens progressively encode more and more grounded, actionable information. And ultimately, that leads to executable physical actions.
So it's like a pipeline.
Exactly. If you could visualize it, it's a clear pipeline from understanding the request and the scene to actually doing the thing.
Okay, and this is where it gets really interesting, right? These action tokens.
Yeah.
So an action token is defined pretty broadly as, let's see, any descriptive guidance iteratively generated by VLAs that ultimately leads to action execution.
So it's more than just the final motor command.
Exactly. It goes beyond just the raw physical movement. And here's the key parallel. This is the aha. moment for a lot of people, I think.
Okay.
Action tokens and VLAs are generalized counterparts to language tokens in LLMs.
Ah, okay, like how LLMs break down sentences into words or subwords?
Precisely. VLA models break down complex actions into these actionable units, these tokens.
That's a really helpful way to think about it. Okay. And this framework, this idea, has led to exploring what, 8 main types of these action tokens?
That's right. We're going to dive into each one. But yeah, the main categories are language description, code, affordance, trajectory, goal state, latent representation, raw action, and reasoning.
Wow, okay. Quite a few different flavors there.
Each one offers a different way for the AI to sort of think about and then execute an action in the physical world.
All right, let's start at the top then, language description.
Okay, this one's pretty intuitive, right? It's just natural language expressions that describe the intended actions.
Like telling the robot what to do in English.
Exactly. It could be a high-level language plan, like make a sandwich.
Yeah.
Or it could be much lower-level language motions, like move your arm forward 6 inches.
And the power here seems pretty obvious.
Mm.
It leans heavily on those existing LLMs and VLMs we talked about.
Exactly. Which means you get strong zero-shot planning right out of the gate. Less need for tons of task-specific training.
Right.
Models like Paul-ME or 2.5, they use loads of co-training data, bringing in that rich world knowledge. And for complex, long-horizon tasks you mentioned, make a sandwich, or maybe make the bed, language is almost necessary to break down the problem into manageable steps.
And it's interpretable, right? You can read the plan.
Huge advantage. Language-based plans are inherently interpretable. That allows for human oversight, intervention, which is critical for safety, for trust.
Okay, but what's the catch? It can't be perfect.
No, the main challenge is what the paper calls imperfect expressiveness. Natural language can be ambiguous, especially for really fine-grained control or those dexterous manipulation tasks where you need absolute precision.
Like, pick up the delicate thing carefully is hard to define perfectly in language.
Exactly. And there's also high latency. Running inference on these big language models takes time, which can be a problem for real-time actions.
Okay, so it sounds like language is great for the big picture, the high-level strategy.
Definitely.
But maybe you need something else for the precise, low-level execution.
That's the implication, yeah. Use language for planning, perhaps combine it with other, more precise token types for the actual movement.
Makes sense. Okay, next up, code.
Right, so these are actual executable code snippets, or maybe pseudocode, that define either a whole robot program or just specific atomic operations.
So instead of English, you're giving the robot, like, Python commands.
Sort of, yeah, or commands for its specific API. The power here is that code provides incredibly clear logical structures.
Very unambiguous.
Very. And it can leverage powerful third-party libraries, think NumPy, for complex spatial reasoning, for example.
Ah, okay.
It basically acts as this transparent, verifiable bridge from a high-level instruction like put the red block on the blue block down to the robot's primitive actions. It supports both hierarchical planning and reactive control. We see this in systems that help robots, say, rearrange and restore objects to a previous state.
It sounds very precise, very explicit. What's the downside?
The downside is that code is inherently constrained by whatever predefined APIs the robot has.
Ah, so it only knows the commands it's been explicitly programmed with.
Exactly. And this can lead to brittle runtime execution. Imagine you tell a robot via code to pick up a glass, and the code assumes a nice, flat, grippy surface.
Right.
But if the glass is actually on a slippery or uneven table, even if the code itself is logically correct based on the API, it can fail miserably because the real world doesn't match the API's assumptions.
That sounds like the symbol grounding problem you mentioned earlier.
That's exactly it. The abstract symbols in the code, like grasp object at coordinates XYZ, don't perfectly map onto the messy, unpredictable physics of the real world. And that mismatch can lead to substantial safety risks.
Wow. Yeah, you can see how that would be a problem. So for code tokens, what's the way forward? How do you make them less brittle?
Well, the research is heading towards developing much more comprehensive API libraries, trying to cover more real-world edge cases, and also integrating things like formal verification throughout the code's lifecycle to boost robustness. Plus, enabling interactive debugging so humans can collaborate with the robot when things inevitably go off script. It's about bridging that gap between the perfect code and the imperfect world.
Got it. Okay, moving on to affordance. That sounds a bit more abstract.
It is a little. Think of affordances as spatially grounded representations. So things like key points on an object, bounding boxes around it, segmentation masks showing its shape, or even these things called affordance maps.
And what do they represent?
they capture task-specific and interaction-relevant properties of objects. It's about the AI understanding not just what an object is, but what you can do with it.
Ah, so like this part of the mug is the handle, that's where you grip it. This part of the door is the knob, that's where you turn it.
Exactly. That's the core idea. And this is powerful because affordances bridge visual perception directly with physical interaction possibilities. This really helps with cross-platform generalization because they abstract away the specific robot's mechanics. If the AI knows where to grasp the cup, the handle affordance, it doesn't matter as much if it's using a two-finger gripper or a dexterous hand. The target interaction point is the same.
Okay, that makes sense.
It helps identify actionable regions for tasks like pour tea, figuring out the spout and the opening, or dexterous grasping in cluttered scenes. It's like giving the robot a map of interaction hotspots.
Right. But what are the limitations here?
A big one is that most current models rely on 2D image representations.
Ah, not true 3D.
Exactly. And that often inadequately captures 3D geometry, which hinders really precise control in 3D space. They also tend to encode static object properties.
Meaning they don't account for changes.
Right. They don't model how affordances might evolve over time. Think about a drawer. Its affordance changes dramatically when it goes from closed to open. Current models often miss that dynamic aspect.
Okay.
Plus, like many vision-based approaches, they can be vulnerable to visual perturbations, things like occlusion, where something blocks the view, or motion blur.
So the future for affordances is more 3D, more dynamic.
Pretty much. Learning true 3D affordance representations, modeling those temporal dynamics, how interactions change things, and just making them more robust to visual noise and disturbances, making them less static and more world-aware.
Okay. Our fourth category, trajectory.
Right. This one's a bit more straightforward conceptually. It's basically a temporally ordered sequence of spatial states.
Like a path through space over time.
Exactly. Capturing the dynamic evolution of an object, or more often the robot's end effector, its hand or gripper, mapping out the precise path it should take.
What's the big win with trajectory?
A really key advantage is that they offer a potential solution to the limited robot data availability problem we keep mentioning.
How?
Because unlike raw robot actions, trajectories can often be readily extracted from off-domain videos.
Meaning videos not necessarily of robots doing things.
Right. You can learn useful motion trajectories from human videos, or even just videos of objects moving in the world. And there's vastly more video data available than specific robot data.
Ah, okay. Tap into YouTube, basically.
Kinda, yeah. And these trajectory representations show strong generalization capabilities across tasks, even tasks that are semantically quite different. The example given is generalizing from watching wiping a table to being able to slide a block on a desk.
Interesting.
Plus, trajectories are generally explainable. You can visualize the path, which is good for human understanding and debugging.
Seems powerful. What's the catch?
Well, often they have limited 3D expressiveness. Many trajectory representations might only encode position, X, Y, Z, but lack the crucial orientation, information role, pitch, yaw.
Which you definitely need for most manipulation tasks.
Absolutely. There's also often computational inefficiency because generating these complex trajectory sequences can be demanding. And VLMs tend to output low-frequency waypoints, maybe just a few points along the path.
Which isn't smooth enough for real robot control.
Exactly. You need a much higher frequency of control points for smooth, continuous motion.
So with trajectories, the win is leveraging vast video data, but the challenge is getting that full 3D detail and smoothness.
That sums it up well. Future work is focused on integrating that full 3D spatial information, developing lighter weight, faster generation models, and maybe creating hybrid action tokens.
Hybrid, like combining trajectories with...
Yeah, combining trajectory waypoints with higher level semantic concepts like grasp here or increase force now to add more nuance and efficiency.
Okay, interesting. Next up, goal state.
Right, so a goal state token is essentially a predicted future observation. It could be an image, maybe a short video clip, or even a 3D point cloud.
And it represents...
It visually represents the expected outcome of an action sequence. It's like a robot imagining, what should the world look like after I successfully complete this task?
Ah, okay. Like picturing the clean table before starting to wipe it.
Exactly. And this approach is pretty powerful because it's inspired by how we humans often think, right? We envision desired outcomes.
Yeah, true.
It offers potentially great data scalability. One technique mentioned is hindsight relabeling.
What's that?
It basically lets you autonomously generate data sets. You let a robot flail around, record what it does, and then after the fact, you can label states it reached as goals for the actions it took to get there.
Yeah.
You create labeled data without needing explicit success beforehand.
Clever.
Yeah. And you could also leverage action-free videos to show the robot a video of the desired end state, like a perfectly made bed. This helps boost cross-embodiment generalization, too, because you can train on goal states achieved by humans.
Okay.
They enhance task specificity. The goal image clearly defines what success looks like and provide robust interpretability. You can see what the robot is aiming for. An example task might be transfer liquid using a pipette, where the goal image shows the liquid successfully moved.
But generating these goal images, that sounds hard.
It is. That's the big catch. It's challenging to generate high-quality and consistent goal states. Often they suffer from overspecification. The generated image includes irrelevant details that confuse the robot or just plain inaccuracies.
Right.
And there's also typically high inference latency. Generating a goal image or video takes significant compute time. One example cited, AVDC, took 10 seconds just to synthesize an 8-frame video goal.
Right.
Another Gen 2 Act runs at only 3 hertz.
Which is way too slow for most real-time control.
Definitely. So the goal state idea has this great intuitive appeal, but the current hurdles are really generation quality and speed. The critical needs are improving computational efficiency for real-time use and finding better ways to handle long-horizon tasks without generating super complex goal sequences.
All right. That brings us to latent representation. This sounds even more abstract.
It definitely is. This involves using purposefully pre-trained latent vector sequences. Think of them as compact, compressed numerical code.
Okay, and they encode what?
They encode action-relevant information over some time interval. They're typically learned from very large-scale data sets. You can think of it as the AI developing its own internal compressed language for representing actions and movements.
Learn from.
Often from action-free internet-scale human videos, or maybe large cross-embodiment robot datasets. This is powerful because it directly tackles the data bottleneck by learning from huge, easily available data sources.
Right, leveraging that web data again.
Exactly, which significantly enhances generalization. It's also very efficient for training the VLA model itself, because predicting this compact latent vector is often much easier than predicting, say, high-dimensional raw actions.
Simpler target.
Simpler target, exactly. And it has strong expressive potential. Because it's a compact numerical representation, it can implicitly capture complex semantics and even integrate non-visual information, like tactile feedback or audio, which is harder for language, or vision-only tokens. It's been used for complex virtual tasks like mining diamonds in Minecraft.
Okay, sounds powerful for generalization and data efficiency, but there's got to be a catch. What's the key limitation here? This feels like the kind of thing that might be hard to understand.
You hit the nail on the head. The crucial insight, especially for you listening, is the inherent lack of explainability and controllability.
The black box problem?
Precisely. Because these representations are so abstract, so latent, it becomes incredibly difficult for humans to look at them and understand what the robot is planning to do or why it's doing it. And that makes intervention or debugging really hard when things go wrong.
Which is vital for safety in physical systems.
Absolutely vital. They also often struggle with inadequate granularity for really fine, dexterous tasks. The compressed representation might not capture enough detail, and there can be issues with incomplete comprehensiveness. Maybe the latent space doesn't cover all possible useful behaviors and potential misalignment with human intention simply because it's so opaque.
So while they have this strong potential for leveraging data,
Yeah, huge potential.
the lack of transparency is a major roadblock right now.
It is. It means that current research often still favors the more explicit forms of action tokens, language, code, trajectories, because you need that reliability and interpretability, especially when safety is involved. The dream is to get the compression benefits without losing human understanding and control.
Makes perfect sense. Okay, number 7, raw action.
All right, back to something more direct. Raw actions are just one or more low-level control commands that can be directly executed by the robot.
Like the actual joint torques or the target end effector position and orientation, the stuff the motors actually do.
Exactly, the real nuts and bolts. The power here is that this is the most direct and executable form. It requires minimal human knowledge or complex annotation. You just record what the robot did.
Seems straightforward.
And it really aligns with this idea called the bitter lesson from LLM development.
The bitter lesson.
Yeah, the idea, popularized by Rick Sutton, is that ultimately the biggest gains in AI have come from leveraging computation and scaling data with simple, general methods rather than intricate human design features. So for robotics, this means end-to-end learning directly from perception to raw action, scaled up massively.
Let the data and compute do the heavy lifting.
Exactly. And early examples like Google's RT1 showed this works surprisingly well. Strong performance on seen tasks, and even decent generalization to unseen tasks just by scaling up the robot data.
Okay, but we keep hearing about data scarcity for robots.
And that remains the massive hurdle here. Data scarcity is still the major challenge for building truly general raw action models. We just don't have datasets anywhere near the scale of text or image data.
Right.
Also, the typical autoregressive models used to predict sequences of actions can suffer from high latency. Predicting one step at a time is slow. And historically, these raw action models showed poor cross-embodiment generalization. Training on one robot arm didn't transfer well to another.
So direct control is appealing, but data and speed are issues. Any recent progress?
Yes, actually, this is an area with really exciting recent breakthroughs. New methods like using diffusion-based action heads, combined with something called action chunking.
Action chunking.
Yeah, predicting short sequences or chunks of actions at once instead of just one step. Models like Octo, and especially you are using this, it dramatically boosts the control frequency. Voyeur apparently achieves 50 hertz control.
Wow, 50 hertz. Compared to...
Compared to older models like RT2, which were around 5 hertz, that's a tenfold increase, getting much closer to real time.
That's a huge difference.
It is. And other techniques like flow matching and real-time chunking help ensure the generated action chunks result in smoother trajectories overall. There's even Voyeur Fast A, which uses discrete cosine transform, like in JPEG compression, for even better action compression and smoothness. And another important technique is knowledge insulation, used in U0.5. This helps preserve all that valuable general knowledge from the pre-trained VLM when you fine-tune the model on the specific, smaller robot dataset. You don't want to lose the common sense when you teach it robot specifics.
So raw action is getting much more sophisticated and performant lately.
Definitely. It's a very active area.
Okay, finally, our 8th category, reasoning.
Right. So reasoning tokens are typically natural language expressions, but they're used differently than the first category we discussed.
How so?
They explicitly describe the AI's decision-making process that leads to choosing a specific action token. They essentially serve an intermediary role. It's like the AI showing its work, its internal monologue made external.
Ah, okay, so it's not just the plan, it's the thinking behind the plan.
Exactly. And the real power here is how this significantly mitigates the gap between high-level instructions and low-level executable actions. By introducing these intermediate thinking steps, it helps the AI connect the dots.
Makes sense.
This really enhances generalization, allowing VLMs to handle more complex, long-horizon tasks. The example given is a robot figuring out how to put the edible object in the bowl, which requires reasoning about object properties, locations, and action sequences.
And like language plans, this must be good for interpretability.
Hugely. Externalizing the thought process massively improves interpretability. You can see why the robot is choosing to do something. This also enables human-in-the-loop capabilities where a person can monitor the reasoning and potentially correct it. Systems like Inner Monologue explore this. It also seems to support cross-embodiment capability, and there are applications being explored even in autonomous driving, like with Drive VLM.
Okay, sounds very powerful for complex tasks and transparency. What's the trade-off? Speed again.
Speed is definitely a major one. Adding explicit reasoning steps leads to increased inference time and reduced execution speed. Thinking takes time, even for an AI. This is a critical constraint for tasks needing instant reactions. Also, in many current systems, these reasoning steps are often fixed manually by the designers, which limits flexibility. The AI isn't dynamically generating the reasoning structure itself, and similar to language data, building high-quality, large-scale reasoning data sets, examples of AI thinking processes remains costly and challenging.
So reasoning tokens are best suited for tasks where deliberation is more important than raw speed.
That seems to be the case, yeah. Complex, deductive tasks that can tolerate lower execution frequencies benefit most. Future work is looking into things like action token-based reasoning. Maybe the reasoning steps themselves are composed of other token types, and adaptive test time computation, where the AI decides how much reasoning is needed on the fly.
Fascinating. Okay, we've covered all 8 types. It's really clear that no matter which token type you use or combination, they all absolutely depend on data.
Massively. Data is the fuel for all of this.
Which brings us to what the source calls the data pyramid for VLA. It sounds like a structured way to think about the different data sources.
It is. It describes this hierarchical, multi-source data paradigm that's really crucial for training these complex systems effectively.
Okay, so what's at the top of the pyramid?
At the very top layer, the broadest layer, you have web data and human videos. This provides vast amounts of general common sense knowledge and implicit mappings between situations and actions just by observing the world.
Right. Learning how things generally work.
Exactly. Data sets like Ego4D, which have hours and hours of first-person human video, are really valuable here. That egocentric view helps reduce the embodiment gap. It's closer to what a robot might see.
Okay, top layer. Web scale, general knowledge. What's in the middle?
In the middle layer, we find synthetic and simulation data. This offers scalable, structured, task-centric data.
Generated in virtual worlds.
Right. Environments like Robocasa or the Agibat digital world allow researchers to generate huge amounts of data for specific types of tasks, learn compositional skills, and experiment rapidly without breaking real robots.
The sim to real.
That's the big challenge here, always. What works perfectly in a clean, predictable simulation doesn't always transfer smoothly to the messy, noisy, unpredictable physics of the real world.
Right. Which leads us to the bottom layer.
The critical foundation, real-world robot data. This is described as truly the most critical resource.
Why? Because it's grounded.
Exactly. It's essential for learning physically grounded, executable policies. It captures the complex dynamics, the sensory noise, the weird friction effects, all the stuff that's hard to simulate perfectly. Large data sets collected from actual robots like XE, RT1, Droid, RH20T, these are invaluable, even if they're smaller scale.
So you have this pyramid, broad web data, structured sim data, and crucial real robot data. But the overall picture for robot data is not great.
That's the sobering reality, yeah.
Yeah.
The overall quantity of real-world robot data is severely limited.
How limited?
The estimate mentioned is staggering. Only about 1,200,000th of the data volume used to train large language models.
Wow. That is tiny in comparison.
It's minuscule. And it's not just quantity. Robot data often lacks sufficient modality coverage. Not enough tactile data, not enough audio data. And it's fragmented across diverse and often incompatible embodiments. Data from a Rethink Sawyer arm doesn't directly apply to a Franca Emika arm,
Yeah, it makes it hard to pool data. So given this pyramid and the scarcity at the bottom, what's the strategy? How do people actually train these VLA models?
The prevalent strategy, the practical solution most use, is hierarchical. It's large-scale pre-training on abundant simulation or web scrape data, get that broad knowledge for the top two layers, followed by fine-tuning on smaller, high-quality, real-world data sets from the bottom layer.
So learn general stuff broadly, then specialize on the real robot data you have.
Exactly. It's a way to balance acquiring that vast common sense and world knowledge with the need for precise, real-world grounding for actual robot operation.
Okay. That gives us a good sense of the current landscape. But where is this all heading? What's beyond the current VLA models and action tokens in the bigger quest for AGI in embodied AI?
Right, looking ahead, one major shift is thinking from VLA models to VLA agents.
What's the distinction?
Current VLA models mostly focus on that direct mapping, inputs to actions or action tokens. But truly general intelligence, especially for complex, long-horizon tasks, requires more integrated agent-level systems.
Meaning they need
Things like persistent memory, sophisticated planning capabilities that look further ahead, and mechanisms for reflection, learning from past mistakes. We need to think beyond these linear input-output architectures towards systems that can adaptively invoke different modules or token types as needed.
more flexible, more strategic.
Exactly. And this also leads towards needing multi-agent systems, where robots collaborate, and designing for human-agent coexistence, where robots can act as capable, understandable teammates for people.
Another big shift mentioned is from imitation learning to reinforcement learning.
Yes, this is crucial. Most VLA models today are trained using imitation learning, basically, learning to mimic human demonstrations or other data.
Copying what they see.
Right. But imitation learning is inherently limited by the quality and capabilities of the human demonstrators, and the data might be suboptimal. You're only as good as your teacher.
Makes sense.
The future likely lies more heavily in reinforcement learning, or RL, where the agent learns through trial and error, optimizing for a reward signal. This has the potential to achieve more robust, dexterous, and high success rate behaviors that might even surpass human capabilities on some tasks.
But RL in the real world is hard, right?
Extremely hard. The challenges are significant. High reset cost when an experiment fails. Low interaction efficiency. It can take millions of trials and, critically, major safety concerns during exploration. You can't just let a powerful robot flail around randomly trying things.
Yeah, that seems risky.
So we need breakthroughs in highly efficient RL algorithms, sample-efficient methods, and developing automated reward functions or ways to specify goals safely without constant human supervision.
And then there's the hardware again. You mentioned from restrictive hardware to full dexterity and modalities.
Absolutely. We touched on it earlier, but it's worth re-emphasizing. To move towards truly general-purpose agents, the research must incorporate dexterous hands that can manipulate objects with human-like skill, going way beyond simple parallel grippers.
New bare hands.
Definitely need better hands. And we need to expand beyond just vision, language, and action. We need to integrate tactile sense, the ability to feel texture, pressure, slip, and audition hearing, and maybe even olfaction, smell, and gustation, taste for some applications.
Wow, a robot that can feel, hear, maybe even smell.
Imagine a robot that can feel if it's gripping a fragile object too tightly, or hear a spoken instruction from across the room, or smell a potential gas leak. Yeah. That requires integrating many more sensing modalities.
That really paints a picture of a much more capable agent. Finally, and this feels incredibly important, the shift from capability-centric to safety-aware.
Paramount. Absolutely paramount. As these agents start interacting more robustly and autonomously in the physical world, embodied intelligence introduces unique and serious safety challenges.
Because they can actually affect the physical world.
Exactly. We're talking about potential physical damage to hardware, damage to the environment, and even, critically, potential harm to humans.
Yeah.
Safety cannot be an afterthought. It absolutely must be a first-class concern woven into the design and development process from the very beginning.
Right. Baked in, not bolted on.
Precisely.
Okay. Wow. And there you have it. We've just gone through a really fascinating deep dive into these vision language action models. We've unraveled how robots are starting to learn to interpret the world and actually act within it.
Yeah, from those granular action tokens, language, code, trajectories, all of them guiding their moves.
To the massive multi-layered data sets that train them and this really ambitious path towards true embodied intelligence.
It's quite a journey. And thinking about how far these VLA models have come, the incredible complexity they're beginning to handle, that interplay between abstract understanding and concrete physical action. What really stands out to you, listening right now, about how these action tokens are shaping the future of robotics? And maybe even shaping our own understanding of what it means for an AI to think step by step, but in the physical world.
It's a lot to chew on. And really, this deep dive is just scratching the surface of this incredibly dynamic field, the pursuit of general-purpose embodied AI, where the models, the data, the hardware all evolve together synergistically. That really does feel like the next great frontier for the foreseeable future.